Hello everyone, this is going to be the start of a series of lectures pertaining to biophysics for the college level. This lesson will cover an introduction into physical parameters, getting into translational and rotational motion, and then relating some concepts into body levers, or treating certain parts of the body as levers as in physics. Some basic parameters when it comes to physics is that usually all of our measurements can be broken down into either scalars or vectors. And a scalar is simply any quantity which can perfectly be described with only a magnitude. In essence, its properties do not depend on the direction that measurement is being applied. Some examples include mass, whether we have 5 grams of water in the traveling north or traveling south, doesn't matter, it's still 5 grams. We use it the same in any calculation. Other scalars include volume, speed, distance, density as well. No matter what direction we're going, the density of a material is always the same. Vectors are a little different in that they are quantities that need both a magnitude and a direction. Some examples include velocity. It's very important if we know not just if we're going 5 meters per second, but are we going 5 meters per second north or south? That combination of magnitude and direction gives us the vector quantity. Other vectors include displacement, which is similar to distance in scalar notation. Velocity is the vector version of speed, and then there's acceleration, and there's also force, among other types of vectors. So just another example is if we have some object that's traveling 5 meters per second, it doesn't matter if it's traveling to left or right, or the positive direction of an axis versus the negative direction. If we're just looking at speed, all we care about is that magnitude of 5 meters per second. When it comes to velocity, let's say that object is traveling in the positive direction of some axis. Well, to give it a direction, we would say positive 5 meters per second, the 5 being the magnitude and the positive sign being the direction. If the object was traveling negative 5 meters per second along some axis, then that's 5 meters per second in the negative direction, or negative 5 meters per second for its velocity in that scenario. And here we're going to look at some information that we can pull from a position versus time plot, looking at essentially if we have some ruler that goes from, say, -8 to 6 meters, or if we're just traveling along some straight line, let's say we're starting at some position 4, whatever that is, 4 meters away from some neutral position. And what this plot says, that is from 0 to 2 seconds, that object is staying still. It has not moved from that initial position. And then from time t equals 2 seconds to 4 seconds, it travels backwards to the -6 meter position. And then from time t equals 4 to 6 seconds, it starts moving forward, and then eventually reaches the neutral 0 position. That's how to interpret this position versus time plot. Some valuable information we can get, whether we just care about the scalar quantities or the vector quantities. If you're asked to solve for distance, all that is what is the total distance that was walked backwards and forwards. And for that, we just need our y values for each linear region. For example, for that 0 to 2 seconds, we started at position 4 and we ended at position 4. So the absolute value of 4 minus 4 is 0 meters traveled. Now from time t equals 2 to 4 seconds, we started at position +4 and we ended at position -6. So the distance traveled would be the absolute value of -6 minus +4, or 10 meters total traveled backwards. And then we'll add to that the final leg of our plot, which went from -6 to 0 meters. Therefore, the absolute value of the difference from the end to the start would be 0 minus -6, or 0 plus 6, which the absolute value would just be 6. Therefore, the total distance d that was physically walked or physically traveled is 60 meters. Some objects stayed still for 0 for a few seconds, moved 10 meters, and then moved again 6 meters for a total distance of 16 meters. If we were asked to solve for its displacement, all we care about is, from some time range, what was its initial position and what is its final position, and take the difference of the final minus the initial. And we're just looking at y values. So after 6 seconds, our object ended at the 0 meter mark. It started at the 4 meter mark. So overall, the displacement was 0 minus 4, or -4 meters. In other words, overall, the object traveled backwards 4 meters when it comes to the grand scheme of things. Because displacement is a vector, we need it to have either a positive or negative sign to give it its direction. Some further quantities that we can pull from a position versus time plot include average speed, which is simply the distance traveled divided by the time it took to travel that distance, which if we traveled 16 meters and it took 6 seconds to do so, then the average speed is 2.66 repeats meters per second. Average velocity is similar, but instead of distance, we use displacement and divide that by time. Therefore, average velocity can also be a positive or negative value. It can have a direction. So -4 meters for the displacement divided by 6 seconds gives us -0.6 repeats meters per second as the average velocity for this position versus time plot. If we were asked to solve for instantaneous speed and instantaneous velocity, essentially the exact value of its velocity or speed at a very specific point in time, those are very easy to calculate, and it's actually easier to calculate the vector instantaneous velocity first. When it comes to a position versus time plot, the instantaneous velocity is the slope at that particular point in time. So y2 minus y1 divided by x2 minus x1. And for this, we could be asked, what's the instantaneous velocity at time t equals 1 second, 3 seconds, or 5 seconds? All we care about is what is the slope of our position versus time plot at those seconds. Since we have linear regions, let's just find the start and end of those linear regions, because any point in between that linear region is going to be equal to the slope. So if we care about the instantaneous velocity at time t equals 1 second, that would be correlated to this linear region, and we would just take the slope from this point to this point, or +4 meters minus +4 meters, divided by 2 seconds minus 0 seconds, which gives us a slope of 0 meters per second. Makes sense. We're not moving at all, we're staying still, so our instantaneous velocity is 0 meters per second. And that would be true if we were looking at time t equals 1.5 seconds, 0.75 seconds. It doesn't matter that we chose one specifically, just that any point between here and here, the instantaneous velocity is still going to be 0 meters per second. At time t equals 3 seconds, we're somewhere along this linear region, and its slope is going to be -6 meters minus +4 meters divided by 4 seconds minus 2 seconds, which gives us an instantaneous velocity of -5 meters per second. Velocity, again, is a vector. It has a direction, which for this type of calculations, we signify as either positive or negative. So time t equals 3 seconds, the instantaneous velocity, or the slope of our position versus time plot is -5 meters per second. And then for time t equals 5 seconds, or again, it could have been 5.1 seconds, could have been 4.9 seconds. All that matters is at that particular time, we're touching this linear region, the slope of which would be positive 3 meters per second. The reason why we solved for instantaneous velocity first is because instantaneous speed is very easy. It's just the absolute value of our instantaneous velocity at those particular points in time. So the instantaneous velocity or the instantaneous speed at time 1 second, that would be the absolute value of 0 meters per second, which is still just 0 meters per second. At time t equals 3 seconds, the absolute value of the instantaneous velocity, negative 5 meters per second, would be the instantaneous speed, 5 meters per second. And then the absolute value of the instantaneous velocity at time t equals 5 seconds would be absolute value of positive 3 meters per second, which just means that we removed that positive sign which gave a direction, and we just have 3 meters per second. Now, one other thing that we can do is position versus time plot. The slopes are what gave us our velocity. Therefore, if we can calculate the slopes of position versus time, we can use that to draw a velocity versus time plot. And if we had a velocity versus time plot, we can use those slopes to draw an acceleration versus time plot. Simply because velocity is the rate of change of position, or position divided by time. Acceleration is the rate of change of a velocity time graph. What matters here is if we had some position plot where some object initially at the 0 position, after 1 second was at positive 5, stayed still until time t equals 2 seconds, and then from 2 to 4 seconds, moved all the way down to the negative 10 position. If you were asked to draw the velocity versus time plot, well, just look at the slopes. From 0 to 1 second, we have this linear region, 5 minus 0 meters over 1 minus 0 seconds, or positive 5 meters per second. Therefore, from 0 to 1 second on our velocity time plot, we have a velocity value that is positive 5 meters per second. From time t equals 1 to 2 seconds, we're staying still. We have a horizontal slope that's just going to be 0 meters per second. Or from time 1 to 2, we're going to shade in this value of 0 from 1 to 2 seconds. And then from 2 to 4, we have this linear region here, which would be negative 10 meters minus positive 5 meters, divided by 4 seconds minus 2 seconds, or negative 7.5 meters per second. Therefore, the velocity time graph from 2 to 4 seconds, we would just fill in the value of negative 7.5 meters per second. If we were asked to go further to draw the acceleration time plot, well, then we would just need the slopes of velocity versus time, which from 0 to 1 second, we have a horizontal slope. Similar from 1 to 2 second, we have a horizontal or 0 meter per second squared slope. And then 2 to 4 second, we'd have a 0 meter per second squared slope. So we would just shade in the value 0 along our acceleration axis for the time 0 through 4 seconds. If we had a velocity time plot that looked more like position in this case, where it had ups and downs, then we would have an acceleration that had actual non-zero values. But just know, to go to velocity, just take the slopes from position versus time. To go to acceleration, just take the slopes of velocity versus time. For example, here we have some velocity time graph that isn't just horizontal slopes. If you're asked to solve for acceleration, just get the slopes of each linear region. From time t equals 0 to 2 seconds, we went from negative 5 to positive 5 meters per second. 5 minus negative 5 divided by 2 minus 0 gives us positive 5 meters per second squared. From time t equals 2 to 4, we have a 0 slope. From 4 to 5, we went from positive 5 to negative 5. So -5 minus 5 meters per second divided by the time range of 5 minus 4 seconds gives a slope of -10 meters per second. From 5 to 6, we have another zero slope, and then from time 6 to 8 seconds, we went from -5 to -10 meters per second. So -10 minus -5 divided by 8 minus 6 gives us -5 meters per second divided by 2 seconds, or -2.5 meters per second. This is all to help us calculate or to draw an acceleration versus time plot, which in this case, we'll just plug in the values of our slopes from velocity versus time. From 0 to 2 seconds, we had a consistent slope of +5 meters per second squared, or a positive slope of 5 meters per second squared. Dash from 2 to 4 seconds, our slope on velocity versus time was 0, so we would just fill that in as such. From 4 to 5 seconds, we had a consistent slope of -10. From 5 to 6, it was 0. And from 6 to 8, our slope on velocity versus time, or our acceleration value, will be -2 meters per second squared. Something cool is that force is related to mass of some object times its acceleration. Since acceleration is a vector that can be positive or negative, force can also be a vector that will be positive or negative. Force is in units of newtons, mass must be in kilograms, acceleration is meters per second or meters per second squared. So if we had some object that was 10 kilograms whose acceleration is modeled here, what is the force that that object experienced at 0.2 seconds, 3.2 seconds, 4.5, 5.7, and 7 seconds? Well, at 0.25 seconds, force is going to be the mass of 10 kilograms times its acceleration of +5 meters per second, because at 0.25 seconds, we have this value of acceleration. 10 times +5 meters per second would be +50 newtons. At 3.2 seconds, we are along this 0 region, so force equals 10 kilograms times 0 meters per second squared, or 0 newtons. At 4.5 seconds, we're somewhere between 4 and 5. Doesn't matter what value, it just matters that of time, it just matters that we're touching this value for acceleration here of -10. So the force that that object is currently experiencing is -10 kilograms, or 10 kilograms times -10 meters per second squared, to equal -100 newtons. And then for 5.7, it would be 0 newtons. And for 7 seconds, we're along this region. It could have been 7.1 seconds, 7.8 seconds, doesn't matter. But we're touching this region right here. Therefore, the force would be 10 kilograms times -2.5 meters per second squared, or a force of -25 newtons. When it comes to vector addition, it's not like scalars, where say if we had 5 grams of something and we mixed it with 5 grams of something, that would be a total of 10 grams of something. For vector addition, we need to make sure that we only add vectors that are parallel to each other. For example, if we had a +5 meter per second vector, represented by some long arrow pointed to the right or positive direction, and let's say we had some -2 meter per second vector, which is represented by a shorter arrow due to the lower magnitude of 2, but pointed in the negative direction. Let's say we wanted the resultant, which is what do you get when you add up two vectors? Well, if they're parallel, just add up their values. +5 plus -2 would yield a resultant of this vector plus this vector of +3 meters per second, which we would represent as an arrow that's a little bit longer than the -2, but a little bit shorter than the +5 due to absolute value magnitudes, but is pointed in the positive direction. Again, we can only add vectors that are parallel to each other. Let's say we want to add up vector A and vector B. Vector A is a 12 meter per second velocity that is pointed to the right and up 60 degrees above our x-axis, and vector B is pointed to the right and down at 30 degrees with a value of 6 meters per second. Whenever we have vectors that are at angles, we don't really use pluses or minuses for the vector to give a direction. We instead have our angle as its direction. That's why we have A equals 12 meters per second at 60 degrees, and B equals 6 meters per second at 30 degrees below our x-axis. The degrees will count as the direction. So if you're asked solve for the resultant of A plus B, we can't just add 12 plus 6 because they're not parallel vectors. Instead, we have to break them up into their component vectors. The component vector is going to be the vector along the x-axis and the y-axis for our vectors. These are pretty simple to calculate. For the x component of vector A, or A sub x, that's going to be the magnitude of A times cosine of 60 degrees. And since that vector is pointed to the right, we're going to multiply it by positive 1. So 12 meters per second times cosine of 60 degrees, which is the same thing as 1/2, times positive 1 gives us a component vector of positive 6 meters per second. Now let's look at vector B. Its x component would be pointed to the right, and to calculate its value, we would take B times cosine of 30 degrees due to this angle, times positive 1 because the x component is pointed to the right. 6 meters per second times cosine of 30 degrees, which is the same as square root of 3 over 2, multiplied by positive 1 would be positive 3 square root of 3 meters per second. Now let's look at the y components. Well, for vector A, it was pointed to the right and up, so the y component, or A sub y, is this upward component. To calculate it, we would take the value of A times sine of 60 degrees times positive 1, the positive 1 being because it's pointed up. Sine of 60 degrees, that's the same thing as square root of 3 over 2. 12 times that times positive 1, we positive 6 square root of 3 meters per second. For the component vector, y component vector of vector B, the component vector is pointed downwards, so this time we're going to use a negative 1 so that we're indicating the direction of the y component. If we had an x component that was pointed to the left, we would similarly multiply by a negative 1 instead of a positive 1. Now then, the y component of vector B would be B times sine of 30 degrees, and because it's pointed down, times negative 1. 6 times 1/2 times negative 1 would equal negative 3 meters per second. Things to note, whenever we're using cosine and sine functions, calculators can be set to either degrees or radians. For this type of math, make sure it is always set to degrees. If you use a website like Wolfram Alpha, just type cosine 60 and then write the word degrees, parentheses, and it will interpret it as degrees. Now then, we have two x-component vectors that are parallel with each other because they're on the same axis, and we have two y-component vectors that are also parallel because they're on the y-axis. Therefore, in order to add up vector A plus B, let's add up their x-components and let's add up their y-components. The resultant x-component is just the sum of all the x-components of each vector we were trying to add up together. We only had 2, so we're just going to add up ax plus bx, or positive 6 plus 3 square root of 3, which is approximately positive 11.2 meters per second. For the y component of our resultant, that would be the sum of the y components of all of the vectors we were adding. We just have a and b, so we take a plus ay plus by, or 6 square root of 3 plus negative 3, or 6 square root of 3 minus 3 meters per second, which is approximately positive 7.4 meters per second. Another thing to note is whenever we have vectors, their component vectors have the same units. If vector A was in units of newtons, then its component vectors would also be in newtons. And we can only add up vectors that are parallel to each other and have the same units. Now then, we have the resultant x component and we have this resultant y component. The next thing we'll do is simply calculate the resultant magnitude and its angle. Well, it doesn't matter which one we solve for first. The total resultant vector's magnitude squared would equal the x component squared plus the y component squared. Rearranging our equation, the resultant magnitude would be the square root of rx squared plus ry squared. Just make sure, in case either of these were negative, just make sure they're in parentheses before you square it. So 11.2 meters per second squared plus parentheses 7.4 meters per second squared, and then take the square root of all of that, is approximately 13.4 meters per second. The resultant angle, or the resultant direction, the tangent of some resultant angle is its y component divided by its x component. Rearranging this would be theta of our resultant, or our resultant angle, is going to equal arctangent of the y component divided by the x component. Now, if you use a calculator, you might see a button that says tangent inverse. If you use an online calculator like Wolfram Alpha, just type arctan, parenthesis, y component divided by the x component, and arctangent of 7.4 divided by 11.2. Or if you used a calculator that has the inverse tan function, use it and then ry over rx. That will give us an angle of 33.45 degrees. One last thing to note is when we draw this vector, when we calculated our resultant, we found an x component that was positive, and we found a y component that was positive. That tells us that our resultant vector is pointed to the right from the positive x vector and pointed up due to the y component vector. When we put our x and y together, start with one vector and draw it, and at the end of that component vector, draw the next one. Or we could draw our y component first, and then draw our x. As long as we go from tail to head to tail to head, we can then draw our resultant like so. Because the x was positive, it's pointed to the right, and because the y was positive, it's pointed up. If the x component was negative, we would point it to the left, and if the y component was negative, we would point it down. And so we have our drawn resultant vector with a magnitude of 13.4 meters per second with an angle of 33.45 degrees relative to the x-axis that is pointed to the right and up. Vector addition for translational vectors. The described mathematics will work for solving for the resultant vector of any sum of translational vectors. For example, if we had multiple arrows, whether they're going up, down, left, right, or at angles, the math we just did would work for all of those translational vectors. Some examples include the resultant of multiple velocities, which would have units of meters per second, the resultant of multiple accelerations, which would be meters per second squared, and the resultant force, or the addition of multiple forces, which would be in units of newtons. For example, let's say we had three vectors, vector 1, vector 2, and vector 3, represented f1, f2, and f3, and their respective angles theta 1, 2, and 3. You might be asked, solve for the resultant vector, or the resultant force of fr, which would be the resultants f1 plus f, or the forces of f1 plus f2 plus f3. This arrow above just means we're adding vectors. That arrow above a quantity just means it is a vector. So the magnitude for FR would just be the square root of our resultant's x component squared plus our resultant's y component squared. Theta, or our angle, would be our tangent of our resultant force's y component divided by the resultant force's x component. Again, just note that if you use a calculator, make sure for these specific types of trigonometric functions, it is set to degrees instead of radians. And if you're using Wolfram Alpha, just type in sine 60 degrees in parentheses or cosine 60 degrees. Just include the word degrees and then it will calculate it correctly in the right settings. To add up those three forces together, we have to calculate all of their x components and all of their y components. Well, f sub 1x, its magnitude, its original magnitude f1 was 10. Its angle was 30 degrees, so to solve for the x component, we use cosine. And because it was pointed to the right, like so, it will have -1 right here. Cosine of 30 degrees, that's like square root of 3 over 2, which multiplied by -1 is negative, multiplied by 10 is -5 square root of 3. The x component of force 2. This force vector has a rightward direction on the x-axis, so that would be positive 20 times cosine of 60 degrees times +1, because it points to the right, would equal +10 newtons. And then the third force has an x component that's pointed to the right, hence the +1. Its value is 8 over square root of 2. Cosine of 45 degrees is just square root of 2 over 2, so the square root of 2's cancel. 8 divided by 2 is 4. The +1 gives it a positive direction. If we add up all those force components together, if we add them all together, we get 10 plus 4 minus 5 square root of 3, or 14 minus 5 square root of 3 newtons. For the y components of these three original vectors, we're just going to be using the sine function instead of the cosine function. And anytime that we have a vector that's pointed up, then we'll times it by +1. If we have, say, for vector 3, that's pointed down in a downward direction on the y-axis, we're just going to times that by -1, like so. So f1y is going to end up equaling +5 newtons. f2y will be positive square root of 3, or 10 square root of 3 newtons. And f sub y would be -4 newtons. Cosine of 30 degrees would be negative square root of 3 over 2. Sine of 60 degrees would be square root of 3 over 2. Cosine of 60 degrees is 1/2, just like sine of 30 degrees is 1/2. And cosine of 45 degrees and sine of 45 degrees both equal square root of 2 over 2. Hence, for those type of maths, I usually have some square roots in the magnitude in order to cancel out with a square root later. Sometimes, but not always. If we add up these three values, we end up getting 5 minus 4 plus 10 square root of 3, or 1 plus 10 square root of 3 newtons. As best as possible, it's good to have the exact value and not round these to decimals, unless you want to, say, round them to 3, 4, 5 decimal places. So the resultant magnitude for a resultant force, we already calculated that F sub Rx is 14 minus 5 square root of 3. Just to give some reference, that's about positive 5.3397 newtons. And F sub Ry, the y component of our resultant, is 1 plus 10 square root of 3 newtons, or to visualize that, that's about positive 18.3205 newtons. In other words, when we draw this, we're going to have a resultant arrow that's pointed to the right due to its positive x component and pointed up due to its positive y component. Solving for our resultant force, let's put the x component in parentheses and square it, put the y component in parentheses and square it, add up those two values, and then square root the sum. that gives us an exact value of 2 times the square root of 143 minus 30 square root of 2, or more visually, approximately 19.08 newtons. The resultant angle of these two components are going to be arctangent of the y divided by the x. Just plug in the exact values, parenthesis 1 plus 10 square root of 3, parenthesis, divided by parenthesis 14 minus 5 square root of 3, parenthesis, and then all that in parentheses for the arctan function gives us an angle of 73.75 degrees. And if you were asked to draw the resultant force, well, since its x component was positive, draw a rightward arrow. And since the y component was positive, at the end of the x component, draw an upward arrow. The magnitudes being relatively proportional, 5 would be a short arrow, 18 would be a much longer arrow. And then from the tail of the first component vector you drew to the head of the final component vector, draw your resultant. Again, it doesn't matter if we draw the x or y component first. For example, if we had our y component, it would be around here. And then from the head of that, we would draw the tail of the x component, which would still lead us here. And the tail of the first component to the head of the last component still gives us pointed up and to the right. We would give it its value, which if we want to round it, that's about 19.08 newtons. And we have to include the angle between the x-axis and our resultant, which in this case would be 73.75 newtons, or degrees. Getting into Newtonian laws of motion, there's some talk about adding to these, but the main laws that he looked at was the first, second, and third laws of motion, which can be represented mathematically. Usually it's best to actually look at the second law first, which just says that force is proportional to acceleration. Mathematically speaking, that means that force of some object is equal to its mass times its acceleration, with force in units of newtons, mass in units of kilograms. If you're given grams, divide that by 1,000 to get kilograms, and acceleration in meters per second squared. Force equals mass times acceleration, F equals ma. The first law of motion just says an object's current linear trajectory will not change unless a net force acts upon it, i.e., the direction is not going to change if acceleration equals 0 meters per second, which is true whenever the velocity is constant. For example, if the object is at rest, it has no acceleration. If the object has constant speed or constant velocity, say positive 5 meters per second in one direction, or it's constantly positive 5 meters per second in the other direction, the acceleration would still be 0 because of the slope. Therefore, there's no net force acting on the object, whatever direction it's currently going, or if it's staying still, it will stay going in that direction. The third law of motion is just that for a force action results in a reaction of equal magnitude in the opposite direction. For example, if we have some block that is on a flat surface, the reason why that block is staying still is because while there's a force of gravity pulling down on the block, which if we say has a magnitude of 10 newtons, the surface is also pushing back on the block with a normal force of 10 newtons, but in the opposite direction. Hence, the reason why if we have something on a table, it's not accelerating in the y direction whatsoever, because the sum of the forces in that direction add up to 0. If force equals mass times acceleration, if force equals 0, then no matter the mass, acceleration will have to be 0 as well. So that just says if something is staying still, any force that's pushing down is balanced by some force that's pushing up, of equal magnitude, just opposite directions. Now, translational versus rotational motion. A force is a push-pull action that directs an object in translational motion, or in linear motion, up, down, left, right, diagonals. Forces result in objects accelerating linearly. Force equals mass times acceleration. A torque is a spin action that directs an object into rotational motion, either clockwise or counterclockwise spin. Torques result in objects accelerating rotationally, which we represent with alpha. Now, similar to the formula for translational motion, force equals mass times acceleration, we have torque, tau, equals moment of inertia times angular acceleration. Moment of inertia is similar to mass. Angular acceleration is just acceleration, but in rotation instead of translation. So, for example, we have torque, and it is also a vector. It has directions that we have to give a sign. Formally, our torque vector is the force vector times the distance that force is being applied from some point of spinning or point of rotation. For torque, we're going to use the magnitude of force times the distance away from its point of rotation times sine of our angle. So, for example, if we have some force, whether it's pulling or pushing at this point, its distance away from this point of rotation here is d, and the angle between those two vectors is theta. If we have some force that would encourage clockwise rotation, well, we're going to assign that torque with a negative value. If we have some force that would encourage counterclockwise rotation, then we would assign it a positive torque value. So it all goes into whether that torque is going to be clockwise or counterclockwise. Counterclockwise torques will assign as positive. Counterclockwise torques will assign as negative. And then when it comes to vector addition, we could then just add up all of our torques together with the positive and negatives accounting for the direction when we get into our net torque. True static equilibrium is just when the sum of forces on an object equals 0 and the sum of torques add up to 0. In other words, translational equilibrium in newtons, the net force equals 0 when the net acceleration equals 0 meters per second squared. Rotational equilibrium in Newton meters is going to be when the sum of the torques equals 0 Newton meters, which is true whenever the angular acceleration is 0 radians per second squared. Let's look at this sample object. We have some bar of negligible weight. That just means that we do not care about the bar's actual force of gravity from its own mass. We just care about the forces that are acting on the bar. Now, the X spot means that this is where we are going to be rotating. So we care about the distance of each force from this point. What must be the weight of object A for the lever to be in rotational equilibrium, i.e. for the net torque to equal 0? Well, let's look at our forces. We have our applied force 1, Fp1, with a magnitude of 40 over square root of 3 newtons and an angle of 60 degrees. We have our applied force 2 of 10 newtons with an angle of 150 degrees. We have our weight A, which we're going to calculate its weight or its force. Weight is a force. Its angle between our distance and our force, if the force is going straight down, this is going to be 90 degrees. And similarly, weight B, our bar is horizontal, our weight of this ball is straight down, so the angle is also 90 degrees. If we look at the distances, force 1 is going to be 10 meters away from our point of rotation. Our weight A is 25 meters away. Weight B is 5 meters away. And applied force 2 is going to be 15 meters away, or 10 plus 5. Plugging all of that information in, let's calculate all the torques that we have acting on our object. Well, we have torque from applied force 1. That's going to be its force, 40 over square root of 3 newtons, times 10 meters, times the sine function of 60 degrees. We're still using degrees. And the reason why it's -1 is because let's just take it might be easier just to look at the x component. This force is pointed up, and it's to the left of this point of rotation. So if we point up and then try to go toward our rotation point, we have a clockwise torque, hence the -1. This just ends up being -200 Newton meters. Torque 2 is going to be, and just to clarify, sine 60 degrees, that's square root of 3 over 2. Therefore, the square root of 3's cancel. 40 times 10 times -1 divided by 2 is -200 Newton meters. Torque 2 is going to be the 10 Newton force times the 15 meter distance times sine of 150 degrees times +1, because this force is pointed up. If we go up and then go toward our point of rotation, we have a counterclockwise direction, or +1. Those are going to be, torque 2 is going to have +75 Newton meters. Torque B is going to be 20 newtons due to its weight, times 5 meters, the distance away from our point of rotation, or the perpendicular distance, I should say, and then sine 9 degrees because they are completely at a right angle to each other, the force and distance vectors. And then this force, weights always point down, so we have a downward force, and then as we move down and move toward our point of rotation, we have a clockwise torque, or -1. This is going to be -100 Newton meters. And then torque A, we're trying to find the weight, we're trying to find its force. So if we multiply it by the distance away, 25 meters, times +1, because a downward force that we start arcing toward our point of rotation is going to be a positive or counterclockwise torque in this case. So the best we get is that torque A equals +25 times its weight. Well then, we're told solve for the weight of A, assuming that we're at rotational equilibrium, or that the net torque equals 0. Net torque is going to be the sum of all these subtorques. -200 plus 75 plus -100 plus 25 F of A has to equal 0. Well, combining these numbers, that's -225. Adding that to the other side is going to give us 25 meters times our weight equals 225 Newton meters. Divided by 25, and we have our weight of object A. It has to be 9 newtons in order to make sure that these other three forces and weight A all cancel out when it comes to torque, such that there's no rotation, there's no rotational motion at this point. Now, torques are related to what are called levers, and there are 3 different lever classifications. The point where we can rotate a lever is called the fulcrum. The resistant force is going to be where you have to try to apply effort to counteract. And essentially, resistance is the force opposing the desired direction of motion. The effort is the force needed to oppose the resistance force to move in the desired rotational direction of motion, and lever classes can be divided into either first, second, or third class. First class levers involve the effort and the resistant forces being on opposite ends of the fulcrum, pointed in the same direction. Second class levers, the effort and resistant forces are on the same side of our fulcrum, but our effort force is further away, which means it has to apply a greater torque than resistance. For third class vectors, or for third class levers, the resistance force and the effort force are on the same side as our fulcrum, but our effort force is closer. This motion vector is where are we trying to rotate. In a first class vector, in a first class lever, if we're trying to move this object up, we have to apply an effort here. If we're trying to move our wheelbarrow up, we have to apply an effort up over here. And for the motion, in order to move upwards, to resist this downward resistance, we have to apply our effort such. So yes, the class of lever just depends on how are the resistance and effort forces related to our fulcrum. Now, we can relate these to body levers, like what happens in our arms and legs and whatnot. Let's say we had some example, like our bicep, the tension in our bicep as we're trying to lift some object. Well, if we had our elbow, which has a total of 13 inches away from the point of rotation, at the end of that 13 inches, we have some 50-pound weight. 1.5 inches away from our point of rotation is where our bicep is attached. The angle between our bicep and our distance vector along our arm, in this case, is 60 degrees. We can represent that in vector notation with this basic diagram right here, where we have the weight of our ball pointed straight down. We have the weight of our tension in our bicep pointed straight up. The tension from our bicep is 60 degrees. Similarly, our tension force being pointed straight up is 60 degrees from our distance vector. Our weight pointed straight down, in this case, will also be 60 degrees relative to our lever arm. Therefore, if we plug all that in, for the body lever to be in rotational equilibrium, what must the tension force in the bicep be to maintain the ball at its current angle? In this case, we'll use units of pound-inches instead of Newton meters. Well, the torque of the ball is just going to be its 50-pound weight times that full 13 inches away from our point of rotation. Because this would encourage clockwise rotation, we're going to times by -1. 50 pounds times 13 inches times sine of 60 degrees, which is square root of 3 over 2, multiplied by -1, will give us an exact value of -325 square root of 3 pound inches. Now, torque of our tension force is going to be the tension force times the distance away it's being applied, 1.5 inches, times again its angle, sine of 60 degrees. And because this is going to be encouraging counterclockwise rotation, we'll multiply by a +1. Therefore, the tension times 1.5 times square root of 3 over 2 times +1 would be 3 square root of 3 over 4 times our tension force, Now, our net torque has to equal 0, and that's the torque of tension plus the torque of the ball. Torque of retention is 3 square root of 3 over 4 times the tension force, plus the torque of the ball, which is negative 325 square root of 3. Rearranging everything to solve for a tension force, that's going to give us 325 square root of 3 times 4 over 3 square root of 3, which is just going to cancel the square root of 3's, or 325 times 4 over 3, approximately 433.33 repeats, pound inches. Some other description of lever classes in the body. There's a third class lever. There are multiple classes of levers. This chart is just to show essentially different examples, advantages and disadvantages. For example, for a third class lever, the range of motion is our advantage, and the load moves farther than the effort applied. An example could be the short bicep contraction moving the hand far. Effort is required, but the disadvantage, while the range of motion is an advantage, the disadvantage would be there is effort required. It requires larger effort to hold a smaller load, such as the bicep tension being greater than the weight that's holding the ball, than the weight experienced from holding the ball. Second class example, an advantage would be the effort required, such as a smaller effort will move a larger load. Like when one calf muscle can lift the entire body's weight. The disadvantage being the range of motion, the load moves a shorter distance than the effort. The load moves a shorter distance than the effort, such as a calf muscle contracting farther than the distance the heel would actually come off the ground. An example of a first-class lever where effort is closer to the pivot, the range of motion would be an advantage. The load moves farther than the effort, such as the head moving farther up and down than the neck muscles actually contract, but the effort would be a disadvantage because it requires a larger effort to hold a smaller load. But a first-class lever example where the load is actually closer to the pivot, the effort required is an advantage because a smaller effort will move a larger load, but the range of motion would be a disadvantage because the load moves a shorter distance than the effort. In any case, that's just a comparison of advantages and disadvantages of the lever classes. And just past the 58-minute mark, that concludes this first in our series of biophysics for college, for the college level, post-bachelor's level. And again, likes and subscribes are not required, but they are kind of fun to see. So whatever the case, peace.